Okay, and finally, we can start to define color spaces. So the quantification of this entire story that we have done so far. For instance, if we want to generate an image on a screen, we have to know how much energy we put in the 3 types of phosphorus the screen has. Now, traditionally, the CIE, the standardization body, has also defined 3 standard light sources, monochromatic light sources, that are used as a reference in much of color quantification. And these 3 CIE primaries, as they are defined, so the 3 light sources, are monochromatic indeed, and with wavelengths 700, and this one 550 like, and then the short one. So basically we have a red primary, a green primary, and a blue primary. That is what this amounts to. And they are all monochromatic, so they have only a single wavelength. But now if you would have different screens, you might have slightly different phosphors and so on. So be prepared for the fact that we have to think about how we can go from one definition of color, quantification of color, to a different scheme, depending on the primaries, for instance. But these are the reference primaries the CIE has defined. Okay, back to the 3 retinal cones. We have seen this slide before. Okay, so these are the 3 cones, H1, H2, H3. And now we want to start to quantify this whole concept of light perception. Okay. A first question we will ask ourselves is, given the 3 primaries the CIE has defined, so these 3 monochromatic sources, how could I combine them and give the same impression as a given light source C of lambda? So again, this would be amount of power for each wavelength. And if I use this light source that I want to mimic in a second, I get 3 responses as we saw, because there are responses from the 3 types of cones, H1, H2, H3, to that given light source, giving me the 3 responses. That is what we have seen before. But now we start to play a dirty trick on the system, because we just saw that actually the system can be fooled rather well. As long as we have the same responses, you couldn't tell the difference. So what we'll try to do now is to replace this given light source by this linear combination of the 3 primaries. And we have to, of course, take different amounts of these primaries to get the same impression as C. So we have a certain amount of first primary and 1, certain amount of second primary and 2, and then M3 for the third primary. And we want to choose M1, M2, M3 in such a way that, this combination of the 3 primaries, remember monochromatic sources, is the same as for this probably more complicated light source C. So, the trick is we have to get the same R's, the same responses. So if we replace C by that linear combination and want the same R's on the left-hand side, that should give us these relative amounts M that we need. Okay? So we replace C by this linear combination of the primaries, and we say, now we still want to have the same R's as before, when we were applying C. And then we have to search what the M's have to be to reach that goal. Okay, we can rearrange a little bit the different sum parts here. So we have an integral, basically a sum, and then this sum here. So as long as we make sure that all the dependent parts on the right-hand side, we can switch order as we desire. So we rewrite this expression slightly, and this is the result. So this rearrangement is interesting for us because if you look at the integral, behind every integral we have this product of an h, that's a cone response function, and a primary, p. And we see we have actually 9 of those integrals because we have 3 possibilities for h, h1, h2, h3, and 3 possibilities for P. PR1, P2, P3, so the red, green and blue primaries. So 9 combinations of H and J's that we can actually form. But for the red, of course, we know what H is like, we know P, that's the standard primary. So everything behind the integral is basically known to us. So we can, in an offline fashion, compute these 9 numbers, if you like. So everything can be pre-computed. So it's just a number. Every integral is just a number that we can pre-compute. Okay? In fact, we will order those numbers in a 3 by 3 matrix, where the i's and the j's will define the rows and the columns. Okay, now, we get a very simple problem as a result. We'll now summarize this. These we call the LIGs here. So these different numbers, the 9 numbers. This is the problem we have. So we have to find the different m's, as I said before, from this kind of equation. That's a very simple equation. This is simply a system of Kramers, so linear equations. So it's rather easy to get m out of this. M vector, m1, m2, m3. Because we need to know for each primary how much of it we have to take. Now, if we start to change primaries, suppose you go to a certain screen, you want to generate the same color, you have 3 different primaries, let's say 3 other monochromatic sources in that case. So how can you make the modification? So what will now be the m's, the amounts you have to apply to each of the 3 new primaries? Well, that's all very simple, actually. So this is the old system. This is the 3 by 3 matrix. So the LIJs ordered now in a 3 by 3 matrix. LM gives is R. And now we want to have the same color, same R. But with different primaries. So all these integrals will change a little bit. These 9 numbers, this 3 by 3 matrix changes because we have now a different screen, different primaries. So we have L prime rather than the original L for the different primary sets. And so accordingly, we'll now also have to apply or take different amounts of the 3 new primaries to get the same color. You can see that if you have solved for these m's here, you can just linearly, because both are 3 by 3 matrices, you can linearly derive from m the new primary, the new amount for the new primary set. So everything is linear up to this point. Okay. Now, the further discussion of color actually involves 2 normalizations. And the first thing is we go now from these m values, this amount that we have to take of each of the 3 primaries, to the so-called twist-stimulus coordinates. And to do that, we have a first normalization, where white, a standard white, is actually used as a reference. So the question here is, which m's would you have to apply to get a certain standard white? More about that in a second. Which m's, how much of each of the primaries would you have to take to mimic this white? These 3 m's we call w's. So you have w1, w2, w3. These are the amounts of the primaries, the CIE primaries, we have to take in order to get the standard white. Now, if you come with another light source, we have 3 different values m. And what we do is we refer to those in this manner. So actually a twist-stimulus coordinate gives you a ratio between the amount of a primary you have to take to get the same impression as a certain light source over the amount you have to take of that same primary to mimic white. Now why does one do that? Because these stimulus coordinates now give us already a feel for color. They tell us whether there is maybe more red in this light source than in white and less green. That starts to indicate the overall kind of color just from the numbers. So it's maybe a little bit more intuitive than to interpret the three stimulus values rather than the M values that we started off with. So we refer to the standard wide. Now, I promised you more information about the standard wide. The standard wide, the CIE wide, so CIE also defined this wide, is a source with a flat spectrum over all the different wavelengths, and such that we have to take equal amounts with our primaries to get that same impression. But this defines actually the power in the primaries. That on the side. But notice that this normalization, this division by W, is again linear. These W's are fixed. So these are three numbers. And in other words, we get this anisotropic scaling of the M values to go from M to T, from the amounts M to the three stimulus values T. Again, linear. Everything linear so far. So if I change primaries again, but now I want to know how to go from one set of three stimulus coordinates from the original primaries to the new two stimulus coordinates for the new primaries, again the whole thing is linear. Because M would behave linearly if we make the transition, and T is just a linear change of the M's. So at this level, we still have, upon the change of primaries, just a linear transformation. Notice that if our light source would be the standard wide, then of course we would have just one for each of the three stimulus coordinates, with W over W. So if you would look at the three stimulus coordinates, you would know where to find the wide that has been used. It's found at 1, 1, 1. These are the coordinates of wide in a three stimulus coordinate system. Which so far, by the way, is also still three-dimensional. Now a bit more about how people in practice can calculate the three stimulus coordinates for a given light source. C of lambda. So typically a light source will have multiple wavelengths, but we start the story by reference to what we need to do to mimic the impression of monochromatic light sources. So what you have here are these spectral matching curves, Tj that we will derive, so T1, T2 and T3. So here we have the value of these curves, and horizontally we have again different wavelengths, as before, from short to longer. And now we have to imagine, suppose I have a monochromatic light source of some lambda along that axis. And I want to get the same impression with my three primaries, which of course are also monochromatic light sources in this case, but doesn't matter. So I have a given monochromatic light source with any of those wavelengths here, and I want to combine the three primaries in such a way that I get, for a human, the same impression. You can check that you get the equations that you see here on top. Notice that in this case, the response to a monochromatic light source of our visual system is just the value for each of the cone response functions for that particular lambda, for that particular wavelength. Okay, so here are the answers. So here we see how much of each of the three primaries we have to take to mimic the different monochromatic light sources. So if you're at a certain point, let's say here, you want to know how much of each of the three primaries you have to take. You go vertical here, you see where that intersects the three curves. These are the three, basically the three numbers M or the three stimulus values you have to take in order to get the same impression as that monochromatic source. And we see for different wavelengths, indeed, we have to choose quite different amounts for the 3 CIE primaries. Now, something about this curve you should feel is quite alarming, because as you can see, we don't only have positive values, we also have negative values, like this one. That's the most outspoken bit that is negative. Actually, here, this curve also goes below 0. So we have, like everywhere, almost everywhere, you have one of the 3 primaries being negative, one of the 3 curves, one of the 3 spectral matching curves being negative. And that doesn't work, because what we are now saying is that in order to mimic a wavelength, monochromatic source with a certain wavelength, you have to take a negative amount of one of the primaries. Now this is something you can't do. We cannot take a negative amount of a primary with a negative amount of energy in it. So these negative values we cannot physically realize. And the worrying thing is that there are negative values all over the place here. So it's like you have problems with monochromatic curves, and that's indeed the case. So it's very difficult to get a perfect replica of a monochromatic source with our 3 primaries. So these very saturated colors, monochromatic colors, are in general hard to generate. Now a bit more about it, because the next amazing thing is, okay, here one of the curves goes through 0 and dips into the negative area, so that is not something we can physically use, but why do we then have a certain amount here? It's not just like blank, we don't know what to do, hands up in the air. No, we have here a certain amount. Where are they coming from? That's something we explain next. Okay, by the way, these 3 spectral sampling curves, their use I will explain then on the next slides. What they are actually useful for, why people went through the effort of mimicking these monochromatic sources that are so rare in nature, these very saturated colors. Okay. So here we see negative values. These are colors, monochromatic light sources that we cannot really replicate with our 3 primaries. That's indeed the reality. We can't do it. There's not a magic bullet here that helps us out of this conundrum. So, but why do we have a value? Why is there not just a big question mark here? Well, because in that case, people try to do the following. So you have a target, you have the monochromatic light source with a certain wavelength that you want to mimic. And you have then the 3 responses here. Right? So in the case where you have a negative value, it means that if you combine the target with that particular amount here of that negative primary, but put on the side of the equation, so to speak, so make turn it into positive. So you take the target plus a certain amount of the negative primary, that gives the same impression as the mixture of the 2 positive primaries. So that gives us a certain value. And why the value is important, we'll see in the next slide. We still won't have a value. Otherwise, these curves will be useless to us. Now you can also think like, my God, the CIE, the standardization body, they came up with these 3 primaries, and what is the result? Well, that you have negative values all the time. Oh, great job, people. Well, the reality is, as long as you have these monochromatic primaries, pretty much the same would happen to other choices as well. So this problem can be hardly avoided. So it's not a bad choice of the CIE, it's just something that is bound to happen for the reason we mentioned before. So all these monochromatic reference sources here are very saturated, therefore rare in nature and hard to reproduce, whatever monochromatic primaries also that we choose. Okay, here we see the use of the 3 sampling curves that we just had, spectral sampling curves. T1, T2, T3. These three guys here, okay? So, because now, if you have these curves, it is much easier to calculate the two stimulus coordinates that we will get for a light source, C of lambda. So here it is again, our general light source C of lambda. You want to know what are the two stimulus coordinates for that light source. Well, what do? You split actually again, same old trick. You split up for every wavelength, and you multiply with the amount of primaries you would have to take to generate the same impression, impression for that wavelength, for the power that we have of that wavelength in our source, C lambda. So again, it's really a combination trick. So we just split up according to the wavelength, and then for every wavelength we see what would be those spectral matching curves, and then we add up and get the two stimulus coordinates of the light source C of lambda. From that, let us calculate the three stimulus values for just any light source C of lambda, based on the spectral matching curves that we derived. Okay, I talked about two normalizations before that we have in the quantification of color. We already had a first where we make that reference to white to go from the M values to the two stimulus coordinates, capital T. Now we go to chromaticity coordinates. Thinking about it, the two stimulus coordinates were not really color coordinates, in the sense that the stimulus coordinates would still contain information about the brightness. Right? So if we add all the M values for a certain light source with 10%, also the T coordinates, the two stimulus coordinates will go up, and we basically only increase the brightness, not the color, of our light source. So there's still that brightness information in there, and we want to get it out. We want to go to something that is pure color. And that's what the chromaticity coordinates do for us in a second normalization step. And here it is. So now, from the three capital T to stimulus coordinates, we generate these three lowercase t coordinates by dividing every one of the capital T's by the sum of them. It's like peeling out the intensity information. If I multiply all my T's with the same number, I keep the same color, but just brighter or darker. That number will now cancel out, because the same number would appear in the numerator and the denominator. So it's like throwing out the brightness information, only keeping the color information. You may now say, but okay, we still have three lowercase t coordinates. Yes, that's true, but of course, if we take the sum of all three, T1, T2, T3 here, we will always find 1 for the addition. They always sum to 1. By their very definition, as you can see. And that also means that if I know 2 of them, I know the third. So basically, we can drop 1. So you can say we just work with T1 and T2 from now. T3 doesn't matter anymore. It follows from the other ones. So these two chromaticity coordinates specify now the actual color information. The brightness has been dropped out. Now we are talking about hue and saturation only. Note that for standard white, where we had capital T1, capital T2, capital T3, all being 1, for standard white we get lowercase t that are 1 over the sum of 1 plus 1 plus 1, so 1/3. So the color white in the chromaticity coordinate space is found at 1/3, 1/3. That's where you find the reference white with which that particular chromaticity space has been built. And note you can give another definition of what you call white, and you would then get different stimulus coordinates, different chromaticity coordinates. So okay, now we have defined the stimulus coordinates. We go back to the CIE primaries and CIE wide and look at the stimulus coordinates for that particular choice. In that case, we call them RGB. Probably you have heard of these stimulus coordinates already. And also for these RGB, these capital RGB, the stimulus coordinates for the CIE choices of primary and wide, we can define chromaticity coordinates as we just saw. So we take these ratios and that gives us a chromaticity coordinate lowercase r and lowercase g for the CIE choices. And below you see this color space drawn. So here, based on those definitions, you would find, well, in the previous definitions, you find 0, 0 gives us B, there's no red, no green. Here, 1, 0 we have red, and here we have green at 0, 1 for the chromaticity coordinates. Based on mainly these equations, but also what we saw before. Right, so now if you look at this diagram, what are the colors, the different colors that we could see? Well, they're lying in this envelope here. Starts here, follows this spectrum locus, as it is called, and goes back here. So all the colors within this area we can see. By the way, spectrum locus, that is a place where we have all the light sources that are monochromatic, so highly saturated colors. These are so-called lines of purple that we have. Now, these are maybe the colors that we may all see that are lying in this space. But they are not the ones we can generate with our primaries. Because these, again, for the same reasons, can only be generated for positive chromaticity coordinates. And that means only for this small part here. All other places in this, diagram for perceivable colors will have negative values, either negative values for the first coordinate or negative values for the second coordinate. So everything outside this triangle here cannot be generated. Now it looks a bit worse than it actually is, because yeah, this may be a big lobe, but if you look at the colors represented here, they are all pretty much the same kind of green. So you don't lose quite that much. We'll see a bit more about that later. But before we do that, we mention again, all these definitions, the stimulus coordinates, chromaticity coordinates, it all depends on the choice of primaries, and now also white. Okay. And you will therefore also see different systems, different color systems, different quantifications of color. It's not like this is like the one and only unique representation everybody uses. There are multiple representations of color, so you have to be a bit careful what people are referring to. There are many, many examples to be given. We just give this example here, where you make a change from one set of the stimulus coordinates to another one. So we have the RGB to stimulus coordinates, and we go to this XYZ system of the stimulus coordinates. And it has been defined because it, for all the perceivable colors, now only contains positive numbers. That's easier. You don't have all these differences of sign and so on to cater for. Now, this may seem fantastic news because for this new set of primaries corresponding to this X, Y, and Z to stimulus coordinate system, it would seem like we can generate all the colors. Everything is positive, only positive coordinates. What can you ask more? Now the problem is that these coordinates, or these primaries actually underlying that system cannot be physically generated. So they are virtual. You can't really make as phosphor with these characteristics. Okay, so, but anyway, having only positive values was one reason to make that change from RGB to XYZ. Calculation is a bit simpler. Another reason was that at some point there was a transition from black and white television to color television sets. So people wanted to send a signal that would work for both color television and black and white television. And in fact, if you look at the Y coordinate here, so if you multiply this matrix with RGB, you get a Y value, and that Y value can be used to directly steer a black and white television set. That's it. That at least another historic reason for that particular transformation, which is a pure mathematical transformation. There are no physical primaries underlying it, as I said. But just to note, there are all these different color systems that are being used in parallel. Depending on the usage, one may be a bit easier than another. Notice that these two systems, they use the same white, because if you would map 1 or 1, which are the stimulus coordinates for white, CIE white, you get again 1 or 1 for XYZ. So white goes to white. So it did not, here underlying is the same white. And of course, for the system XYZ, you can also have the chromaticity coordinates. So with the usual transformation as we have seen it. And here is the XY, lowercase x and y, chromaticity diagram. You see the original coordinates also here, the 3 primaries that were used for CIE are now lying here, here, and somewhere up there. So these are the original primaries. Notice, however, that everything is in this single quadrant. Everything is positive, both the lowercase x and lowercase y, for all the colors that we can possibly perceive. This is white. 1/3, 1/3. It's also the CIE white. Note that the colors that you could generate with your 3 CIE primaries are actually all the ones lying in the triangle spanned by B, G, and R. And you see indeed that this is area where you start to lose a lot of colors. When drawing the line between B and G, everything falling on the other side there cannot be generated. That falls out of the triangle spanned by the primaries R, B, G. And that's what the colors correspond to. So that would be blue, of course. Then we have somewhere red here. And green would lie somewhere here, the primary. White is 1/3, 1/3. So this is now, again, lowercase x, y. We mentioned spectrum locuses before, where all these monochromatic light sources are placed that we can see but hardly generate or hardly mimic with our primaries. Certainly not in this area here. But they are fortunately very rare in nature, so we don't lose quite that much. So for the European television system ABU, these would be the places where the different primaries are found, the CIE primaries, the EBU primaries. And the same for NTSC, the American television system has different primaries, and they have these coordinates in this lowercase x and y color space. In summary, here you see, in fact, the 2 choices. NTSC we have, EBU we don't have here, but anyway, it's pretty similar. So for different types of screens, for different types of phosphors, you have different types of primaries, you have these three triangles spanning the triangles of a single system, and those systems will only be able to generate the colors that fall within. Note one thing, all the primary choices have typically one bluish color, one reddish color, and one greenish color to span most of this color space. So if you would, for instance, make a bad choice, you would choose one primary in the blue area, one red here, and let's say one orange, you would only be able to generate colors in that triangle. So many colors would fall out. You would not be able to generate a single green, for instance, in this additional system. So one could indeed make a choice of primary so that we have as few colors, as little area in our color space falling outside the triangle spanned by the three primaries. And as we saw, it will typically always imply we take something in the red, one primary in the red, one primary in the red, blue, and one primary in the green area. But another remark is that this space does not really represent perceptual difference all too well. So this is now this XY space that was used in the past, but if you look at perceptual differences, for instance, here we go from green to almost like red in over a very short distance. If you take the same distance, but here you hardly see a difference when going from one to the other. And these ellipses show, in fact, that kind of sensitivity. From here to here, all the colors in that space are more or less seen as the same. And these ellipses get much smaller where you see all these transitions. And the colors in all these diagrams are not fantastically rendered, I have to add. But anyway, if we talk about color in a perceptual sense and perceived color differences, this diagram is still not really doing the trick for us. It's not ideal. So just minimizing the area within the perceivable color space outside the triangle with the primaries is probably not a good idea, because area is not representing perceptual difference. So here we have another example then of a space that gives us a better idea of perceptual difference. By the way, small remark here before we don't go too deeply into it, you don't have to know the details of this, but if you have a chromaticity coordinate space, you find the three primaries used to define that very space at 0, 0, 1, 0, 0, 1. So the primaries are there, and white is at 1/3, 1/3, always. Okay. And what happens if you change these things, if you change maybe the primaries and the white, is that 4 of these points now have to shift, right? So in the new space, the new white would have to be at 1/3, 1/3, and the new primaries have to be at these standard positions as well. And in order to achieve that, if you go from one coordinate system, chromaticity coordinate system, to another, making that kind of changes, the corresponding transformation is a 2D projective transformation. Details are not important, just to mention this. So, and that is what we will do here. We'll now define yet another color space, and this is the new chromaticity color space for these UMV color coordinates, as they are typically called. You see the transformations defined there, how to go from XY to UV. And in this space, typically the same distance corresponds, same distance measured in the space, corresponds much better to the same perceptual differences of colors, although again not perfect. But often when it comes to perceptual differences, when you try to optimize something for human observers, this chromaticity space can, for that reason, be a better space to work in, because distance tends to mean more in this space. But again, yet another color coordinate system. So there are many, just to say. It's not because you see some color coordinates that you exactly know what's going on. You have to know in which space are these color coordinates actually defined.